Welcome back. My name is Funda Günes. I work as a research statistician at SAS Institute. Today I would like to talk about stack ensemble models and how they are used in data science competitions. How many are you heard of data science competitions? Just curious. Yeah, good. I will talk about what they are and how they are using how they use stack ensemble models. This was a collaborative work with two of my colleagues, Russ Wolfinger and Pei. They are both from SAS. Among us, Russ was the one who had a lot of experience with Kaggle competitions. He actually holds a master's status. Only a few people have that status, so it's very impressive. I will talk about what are ensemble models and specifically what the stack ensemble models are. And then we will talk about some common problems in building predictive models, like overfitting, information leakage, and how we can avoid them by using some techniques that best practitioners always use, like cross-validation, regularization, and bagging. And in the second part of my talk, I will talk about SAS visual data mining and machine learning, show you some examples. An example that we built to build a stack ensemble model, it's going to be a 3-level stack ensemble model. So let's start with defining ensemble modeling. Ensemble models are commonly used to boost prediction accuracy by combining predictions from multiple machine learning algorithms. The traditional way to do is so-called combining weak learners, but the modern way is to do first create a strong, well-chosen library of models and then combine them. So strong yet diverse models to have that in the model library, that's the goal. So that has many parallels in building successful human teams in business and sports. Every team member makes a significant contribution, and the weaknesses and biases of the other contributors are offset by the different team members. And the simplest kind of ensemble modeling is the weighted average. Suppose you have 3 predictive models, like you see here. One is coming from a decision tree, another coming from a support vector machine, and the last one is a neural network model. In a simple weighted ensemble, all those models take the same weight. So if you have a target, which is interval, this entails to dividing the predictions that comes from 3 of those models by 3. But more generally, you can think about using weighted average. You might believe that some of those models are stronger than others, and you might go ahead and manually give higher weights to those models. But probably the best approach here is to estimate those weights by using another level of learning algorithm, and this is called stack ensemble modeling. Before I go and talk more about stack ensemble modeling, I would like to show you some examples where ensemble modeling is used. In decision trees, it's commonly used in the random forest model and the gradient boosting model. In a random forest model, a diverse set of decision trees are built on different training sets, where each training set is generated by bootstrap sampling, which is simply sampling with replacement from the training set, but only using 2/3 of the training set. And in the gradient boosted trees, the decision tree models are successively built on optimizing the residuals that comes from the previous model. And this is a kind of stochastic gradient descent. In a broad sense, you can even think that multiple linear regression is an ensemble model, where each predictions come from a simple linear regression and the weights are formed by linear regression. So going back to model stacking, so you have 3 predictions coming from 3 models, and these are used as input in a second level modeling algorithm. The second level modeling algorithm is optimally trained to minimize the loss function and produce a new set of predictions. Commonly, as a second-level algorithm, linear regression models or logistic regression models are used, but this second-level algorithm is not only restricted to regression. You can use any kind of machine learning algorithm, which opens the door to other nonlinear ML algorithms. So you might have noticed that ensemble modeling and model stacking are especially popular in data science competitions, in which a sponsor posts a training data that includes labels and a test data that doesn't include labels. And there is this competition to produce best predictions on the test set. Often individuals, teams, they build their own ensemble models, and towards the end of the competitions, teams get together, they join forces to build even stronger models. One popular data science competition is Kaggle. You can explore numerous winning solutions by going to their website and just look for winning solutions for different competitions to get the flavor of the state of the art. Another one is KDD Cup. I looked for KDD Cups this year competition, and it is about traffic congestion in China. I wanted to see what they use. The competition took place, I think, somewhere from February to June. I wanted to see how they use ensemble modeling, but I couldn't get much information because it was all in Chinese. It was hosted by the Alibaba group, so I will definitely ask one of my Chinese friends to help me understand what techniques they use there. But this is the result from 2015 KDD Cup. They use 3-level stack ensemble modeling. Okay. So this is their model library. They build a diverse set of models, 64 models, by using gradient boosting. The green boxes shows the gradient boosting models. These are the neural network models. The orange ones are factorization machine models and regression models and so on. So at this stage, they build all those different models, and you can see that there are multiple gradient boosting models. They probably differ in their use of hyperparameter settings, the number of feature sets, even the training sets. So the goal is to create as diverse as possible to be able to produce models that generalize well to a new data set. And at stage 1, those 16, the predictions that comes from those 64 models are used as inputs to generate 15 different new predictions that comes from these 15 models. And among those, like you see that 7 are gradient boosting models. And the popular XGBoost algorithm is used that. It's very, and we have a similar implementation of that in SAS. I will show in an example of that soon. So this was stage 1, and you have like 15 predictions coming from stage 1, and they are used as input in a stage 2, stage 2 model here, which are gradient boosting and linear regression model or logistic regression model. And then these two predictions are combined in a single model with the regression model. Question?
What's the intuition, or why is there so many gradient boosted models and so few?
Because they're so powerful. They were really good. They were like the winning solution for many of the supervised algorithms that people use. And I will talk about how you can get different models by how you can enhance diversity in the next slide. So they are not all the same models. It's like you see here, there are like 7 different feature sets, and they use different hyperparameter settings, different even input variables. Those models, they are not using the same input variables. So the goal here is to create as much as diversity so that, you know, the model that we train would not overfit to our training data. And I will talk more about that in this slide. So to build a powerful predictive model like this, the diversity is the key. And there are various ways to enhance this diversity using different machine learning algorithms. For example, if you have like decision tree models, like gradient boosted models or forest model, it's always a good idea to put a factorization model there because it's trained in a different way. And also different machine learning algorithms has different strengths. And you can also, within the same algorithm, you can set different hyperparameter settings because they have like multiple local optimums. And you can use different feature sets. One simple techniques that I use, just simple random sampling on the feature sets, like 50% of it, even less. Also, you can do this in a more principled way, like Raywan told at the first before me, and opening the door to this hard and difficult problem of feature selection. You can also try different training sets. So you may ask, like, how am I going to try different training set? I just have one. So one is bagging. Bagging is sampling with replacements from the training set, and it doesn't use all of the observations in the set. And the other one is cross-validation, and I will talk more about that in the coming slides. So again, the reason that we had all those models in the KDD and when we fit a model to has as diverse models as possible to minimize overfitting. So in an overfitting model, if you fit an overfit model to this data, it would look something like this. So we don't want to do that because it won't generalize well to a new data set, right? So we want to have more smoother curves. So these are the same data. The black points are same in both graphs. We want to have more smoother curve just like this. So it will produce better prediction error on a new data set. And other than using different models, a best practice to control overfitting is to assess your models by using cross-validation. And on the next slide, I will talk more about that. But before, the classical way to minimize overfitting is to use a single validation set. It is a reliable method to assess models, especially if this is your final model. And this has been the main technique we use in our SAS data mining product, SAS Enterprise Miner, since its inception. But it has some disadvantages if you are actually planning to use validation set in the model training stage. The biggest disadvantage for me is that, like, when you build a model, it's not that you just need one validation set. You start your data set, you do feature extraction, feature selection, you do model training. So how many validation sets you will have? 4, 5? And every time you get a different validation set, you're decreasing your training set. So if you want to build a competitive model that is highly predictive, you don't want to set aside your data set and reduce your training set this much. The other one is in a single, when you have a single validation set, you have just one single split. Suppose you are using 30% of your data as a validation set and you're doing feature selection. So when you change the split, you might come up with a whole different set of predicted variables or inputs. And also, setting aside one validation set does not help directly in constructing stock ensemble models. So, like, to build stock ensemble models, remember I had predictions that are coming from each model. And for that, we will use cross-validated predictions. So let's talk about cross-validation. In cross-validation, when I talk cross-validation, I talk about k-fold cross-validation. You divide your data into k disjoint folds, And then you hold out one fold of the data and train the model on the remaining part, and you assess your model on this holdout part. And then you do this for the second holdout part, and this is the predictions for the second holdout, predictions for the third holdout set, and so on. So when you combine those predictions that come from all of the holdout sets, you will get one column of predictions that is for your whole training set. And these are called cross-validated predictions. Now, you can use those cross-validated predictions to assess your model, and it is a very good assessment compared to a single split assessment. And also, you can safely use those cross-validated predictions as new input variables when you build a stock ensemble model. So I often get the question, like, how many folds do I have when I do cross-validation? 5 and 10 are commonly used number of folds, but there is no clear answer. It depends on your data size and your how strong signals you have in your data. But remember, every time you increase your fold number, the computational expense is increasing too. Because instead of fitting just one model and scoring for one model, you're doing it k times every time you do it. So Ray-Ban talked a little about the collinearity problem between the predictions, how ML algorithms, like in general, algorithms are not good at dealing with collinearity. And it is even a bigger problem in model stacking, because all those predictors that you use that comes from, they predict the same target. So like from that level 1, they all predict the same target. So they will all be highly correlated to each other. And this makes the overfitting problem even worse in model stacking. And a good practice, arguably, to use regularization when you're training your stock ensemble model. These are some commonly used regularization techniques. And here, your loss function, this is for linear regression. You try to minimize least square errors with subject to this penalty. This is the regularization. And this kind of controls your model weights. So these are different penalties, like L2 norm of the penalties. This is especially good if you have a lot of collinearity. Lasso penalty is very good if you want to fit your model and at the same time do some feature selection to get some interpretable models. Adaptive lasso is very good with very sparse models, and elastic nets is good at identifying group of correlated predictors. At the same time provides the prediction too. So another related problem to overfitting is information leakage. I see this more and more happening in data science competitions these days. In data leakage, the information from the target somehow makes its way to a model building process. And it causes overly optimistic models, and it can be caused by human or mechanical error, but often the models built this way are useless in real life. So it's sometimes intentional, sometimes unintentional. One concrete example to information leakage is this prostate data example. And in thousands of variables in the training data, there was a variable called prosurge. And the target is here if the patient had a prostate cancer or not. So this variable actually is if they had a surgery or not. So if you build a model by using this variable, it's going to be highly predictive. It's going to look overly optimistic. But in real life, of course, you won't have that information to predict if a patient has prostate cancer or not. In many instances, leakage not occur in a subtle and hard to detect ways. And some types of leakage often happens in the feature engineering stage. So that is the stage that you really need to be careful because it's very easy to make a mistake, leak the test data into the training process. So the one good practice is that if you have a test set that you want to use to assess your models, go ahead and just delete those labels for the test set until you're completely done with your analysis to assess it in the last stage. Now let's switch gears to SAS, visual data mining and machine learning. So SAS, visual data mining and machine learning on SAS VIA, offering surfaces in memory parallel computing machine learning techniques such as gradient boosting, forest, decision trees, neural networks, regression, vector machine, and factorization machine. So all those models has different strengths. Gradient boosting models are really popular out-of-box solution. Neural network models are really good with analyzing image data. Regression is very good in ensembling and model stacking. And FactMag is powerful for sparse data and useful for recommendation systems. Actually, this factorization machine model itself was the winning solution for the 2012 KDD Cup, just itself, without ensembling with other methods. So like each of those modeling algorithms comes with a set of hyperparameters that you need to specify before you start to train your model. And these are called hyperparameters because they are not optimized during the training stage. For example, if you are fitting a neural network model, and this is not like fine tuning, like if you're doing a neural network model from scratch, you really need to decide the architecture of your model, how many layers it will have, how many neurons on each level and such. Also, you need to decide the stochastic gradient descent parameters, such as like learning rate, annealing rate. And if you have regularization, what would be the regularization parameters? These are all data dependent. Even you have a lot of experience building models, you won't know which value will be good for a regularization parameter or a learning rate. So in order to navigate this model space and active nearly optimal models, a basic strategy is to fit models on a grid of those hyperparameters, which would give you an infinitely many models. And it is very hard, time consuming. So one of the things we have in SAS data mining and machine learning is that we have this auto-tuning capability embedded in our machine learning algorithms that search for those best hyperparameter tuning, best hyperparameter values for all those parameters using different methods. One of them is just a random search, like giving a random numbers to all those parameters, and it is shown through scientific papers that it is very efficient. But we have also more intelligent algorithms that use like genetic algorithms. At every iteration, it just changes the parameters a little bit and refits the model and assess that by using cross-validation or some other performance criteria. And we recently added Bayesian kriging. This is also very popular in hyperparameter tuning. Yeah, I think I covered everything in the slide. So using those techniques can rapidly reduce the model error that's produced by default. And the great thing is that we can handle this kind of work in our in-memory parallel computing environment. So it is really fast. So next, I would like to show you an example to building a strong library of diverse models and how we fit a 3-level stack ensemble model. So for this, I used one of those UCI repository data sets. I had a binary target and 13 variables, a mix of nominal and interval variables. And you can reach the whole project and the analysis of the data. Everything is available in our GitHub repository. So I'm not going to talk about this much, but I just want to mention about feature engineering. So one of the things we had done with we did a lot of data prep. I'm not going to go into any of the details, but for the feature engineering, I feel like feature engineering is part of the data science that is more of an art than science, and I feel like there is no it's not black or white. There is no like really true answer to this. It is just to use the data. It can sometimes be even an external information to help you get a better prediction accuracy. So commonly used feature engineering techniques include like transformation of numeric variables, like log, square root transformation, sometimes converting nominal variables to interval variables, sometimes converting interval variables to nominal variables. And this was a little hard for me to understand because I have a statistics background. Like, why do you invert a numerical variable to a nominal variable? Because you lose information, right? Number says more. But it is especially useful if you have some outliers in the data. So it just puts them in one category. Also, it is known to be really useful in risk analysis. You can do many other things with the feature engineering. You can generate a new variable that is actually the rankings of those your numerical variables. Possibilities are infinite. So for this data set, because I am a statistician, I thought about using a one-way ANOVA on one of those numeric variables. The numeric variable is a relationship. It has like 6 levels, husband, not in a family, and so on. So these are the frequencies for each level and how much of the data for each level. What I did is that I just fit a one-way ANOVA by using the training target for this variable. And then I obtained those expected mean values for each level. So it actually shows that if you're in a relationship or family, you tend to make more money than if you're not. So those numbers are. So instead of using these labels in my data, which really means anything, I decided to use those numbers. So every time I saw husband, I replaced this with this number. Every time I saw not in a family, so this is a numeric variable. And it actually helped boosting the prediction accuracy. So this is the 3-level stack ensemble approach we took. We wanted to build a really fancy model because we were writing a paper. So we fit like thousands and thousands of models, so it required a lot of bookkeeping of those models, so it was a challenge, but I felt like we learned a lot from this project. In the level 1, we have 4 different modeling algorithms: gradient boosting, forest, logistic, and a factorization machine model. So in this level 1, we just did go, and for each of the modeling algorithm, we found the best set of hyperparameters by using this, our awesome auto-tuning capability in SAS. And then in the level 2, we had here, after we found those hyperparameters, we wanted to increase the diversity, so we generated 100 versions of the training set by using bootstrap sampling. And for each of the bootstrap sample, we fit the model with these hyperparameter settings that we found in the first level. And same for forest, logistic, and factorization machine models. So we have around here 400 models. While we are doing that, we also calculated 5-fold cross-validation, predicted cross-validation out-of-fold predictions. So it is 400 times 5 It is 2,000 models at this stage. And then, so like each of the 5-fold cross-validation gives just one column of predicted values. So in this case here, I just combine those 100 models by using equal weights, just as a simple ensemble model, to create just one average ensemble model for gradient boosting, one average ensemble model for forest, logistic, and factorization machine. So I haven't done stacking yet. All I did here is that I generate different versions of training sets and then combine them by using a simple equal weight ensembling. But now I have these out-of-fold predictions from each of those ML algorithm coming. Those 4 of them, I will use to build stack ensemble model based on those 4 models. And for this, I will use different techniques. I will use regularized regressions. This is simpler regression with like L1 or L2 norm. I will try regularized scalable gradient boosting, and another technique is hill climbing. This is more discrete method. I'm not going to go into detail, but if you're interested, and I can show you some references, it's very efficient in building ensemble models too. So these are my level 2 ensemble model results. So these are the 5-fold cross-validation errors of the 4 average models that I got in the end of level 2. As you can see, gradient boosting is, again, by no surprise, the winning algorithm here too. It's just the error is less than. But it doesn't mean that, I can still reduce this error by using these models, because that's what I will exactly do. I will combine all those models and try to get a model, maybe somewhere errors around here. Try to finish real quickly. So this is, I'm combining those 4 predictions by using adaptive lasso. Raven mentioned this. So you put some penalty on the, when you do minimize as loss function, and it is on the, controls the weights and controls the collinearity. And here we have this reg select procedure. In SAS, we have a lot of procedures that are kind of like wrappers on different functions, like cast functions that we have. And you have a model statement that defines your target, and these are my input variables here. And I'm using lasso selection. I'm using some different criteria, choose a different model. So the result of this model is here. So these are the different weights that each model gets. So mean gradient boosting model, of course, got the biggest weight because that was the most predictive model. But also factorization machine model and force model helped a little bit to get a better prediction error than the gradient boosting model did. And the other method is to use this to restrict the model weights in a linear regression to be positive. And this is shown to be very efficient in stack ensemble modeling too. For this, I use another procedure. Actually, this is from our econometrics product in SAS. And it restricts each of the coefficients here to be greater than 0. And then the results are very similar to adaptive lasso, but you see that here logistic regression model gets a really, really small weight. It didn't appear in lasso model because lasso was also doing variable selection, so it completely eliminated that from the model, but this model doesn't have the ability to give like exactly 0 to regression coefficients, so it just appeared here, but it doesn't play a big role. So the gradient boosting procedure is our implementation of XGBoost. It's very comparable, only there is slight differences. The results are very similar with XGBoost. And here I'm using the auto-tuning capability to find the best hyperparameter values of the gradient boosting algorithm. So all I need to do is just to add this auto-tune statement here, and then specify for which parameters I would like to optimize. And And for this technique, I just use the random sampling technique. Sample size is 200. So it just finds 200 different parameter settings and then fits the model for each of them and picks the one that for which the prediction error is the smallest. And for doing that, it compares those models by using 5-fold average score error, which is mean score error, basically. And then I'm saving my model here. I'm going to show this later in a CAS table. So this is also in memory. That's one of the great things about like having this CAS environment. Everything is in memory, so you don't really need to move data, transfer data, and it just enables you to get a lot of efficiency and performance when you fit many models. So this is the auto-tuning results. You can see the best configurations, the number of trees. My gradient boosting model used the lasso parameter, ridge parameter, and everything. So it shows that what the default objective value was and what the best objective value. So it decreased. And I would like to point out here how much time this took to fit this model. So you might think that I just fit one model here, but I actually fit 1,000 models. So I searched for 200 different hyperparameter settings by using 5-fold cross-validation. So it's meaning 200 times 5,000 different models are fit and scored in 300 seconds. This means like fitting and scoring one model is a fraction of a second, so it's very fast. So in the gradient boosting model, we don't have the model coefficients like you have in a regression model, but we have this variable importance table. This kind of table can be also used for feature selection too. But in this case, again, my gradient boosting model, the most powerful model, it's getting the biggest weight, and the logistic regression, FacMag has a small contribution, but they are helping me to get a better predictive accuracy. So now in this here, I'm using the grad boost statement and reading this saved model information in a CAS table and scoring for a new data set. So like one good practice that I learned throughout this project is that when you do stock ensemble models, you're fitting a lot of models, it has different levels. One good practice is that as soon as you fit a model, just go ahead and score it for your test data set, because dealing with like thousands of data, it really gets hard to bookkeeping all of them. So these are the predictions that I fit to models that were the results of my level 2 models. So I need to use those. Like this is not the original test set. This is the predictions for my test set that are for level 2. That is the input, and I'm scoring for that using this stock ensemble saved model. So now this is comparing the best model from each level. You can see that the test error at each level is dropping. But if you just look at the numbers, you might say, like, does it really worth to try that much? You know, that the test score may not be like that significant for you to give all that effort to try all those stuff, especially going from level 2 to level 3. But as I say, this can make a huge difference. One more minute and I'm finishing. Okay. So it is just because this can make a big difference in a data science competition, maybe not in a business setting, but also we really wanted to build a fancy model, as I said. Like if you just did use the level fun and do simple stacking, you will get something close to this. Not this, but something close to an error that you would get on the level 2. So don't try too hard. Just use a simple stacking model, and you would, using those diversity tools that I provided, and you will probably get much better model than the best model that you had in your model library. So yeah, this is my last slide. We have a paper about this, and we have a GitHub repository that has all the data sets and analysis, and you can also reach online documentation of SAS via at this link. Thank you, sorry that it took longer time.